Question 1. Define electric field strength at a point in an electric field, and this is worth 2 marks. Electric field strength is defined as the force per unit, and this is quite important, positive test charge. Why is it important to write the word positive for the test charge? Well, the direction of the electric field is dictated by the direction that a positive test charge would take. So if you're looking at a positive charge and you were to draw the electric field surrounding that, then a positive test charge placed here would be repelled from that positive charge, which tells us that the direction of the electric field is radially outwards. If, however, we're looking at a negative test charge, then the charge would be attracted towards, because it's positive, this positive test charge, would be attracted towards that negative charge. So the field is radially inwards. If we're looking at a uniform field, let's look at one here, and we have positive plates up here and negative plates down here. Our electric field would be uniform, with edge effects, of course. And the direction the electric field would take would be the direction that a positive test charge would take at any one point. So it's from positive to negative. So that's why it's important to get those 2 marks. We have to write the force per unit positive test charge. B. 6-point charges of equal magnitude Q are held at the corners of a hexagon with the signs of the charges as shown. Each side of the hexagon has a length A. P is at the centre of the hexagon. Show, using Coulomb's law, that the magnitude of the electric field strength at point P due to one of the charges is. In the first question, we were asked to define the electric field strength, and we said that the electric field strength is the force per unit test charge. And that's how you write it using an equation. We know that Coulomb's law is the force between 2 charges, which is this. So we're going to pop this in to here. K, Q, Q, over Q, R squared. These 2 test charges cancel. So we're left with the electric field strength is equal to KQ over R squared. Now in this case, I was using R. They're looking at A. A is the distance between the 2 charges here. If we were to think about a hexagon is made up of equilateral triangles. And that is triangles that all have the same length of side. That means that this side of the triangle is A and this side of the triangle is A, which means the distance between the charges and this point P in the middle at all points is A. I'm going to rub that out just now because I need to keep it clean for the next question, but bear in mind that the distance between the charges and point P is A. I feel like we're going to use that later. 2. On the diagram, draw arrows to represent the direction of the field at P due to point charge A, label this direction A, and point charge B, label this direction B. If we go to point P, that's where our positive test charge would be. So we imagine that's a positive test charge. We can see that A is a positive charge. That means that this positive test charge would be repelled from A, meaning it would be going in that direction, and we're going to label that A. Conversely, B is a negative test charge, and our positive test charge at P would be attracted towards B. That means it would be going in that direction for B. One thing to note is that I've made them both the same size, and the reason I made them both the same size is because they'll be experiencing the same magnitude of force per unit charge based on the fact that everything is the same distance apart. So these 2 arrows have to be the same size. 3. The magnitude of Q is 3.2 microcoulombs and length A is 0.15 metres. Determine the magnitude and the direction of the electric field strength at point P due to all 6 charges. I think we're going to have to draw some more arrows. We've already drawn our electric field strength due to point A. Let's look at the electric field strength due to this charge here. We know that the positive test charge will be attracted towards there, so we'll have an electric field strength in that direction. Now we'll look at this positive charge. The positive test charge will be repelled, and it will repelled away from there in that direction. Now we'll look here. We know that this is negative. We're looking at a positive test charge, so it's going to be attracted towards it. We've already done B. We've circled that already. Let's look at this one. P will be repelled from that positive charge, and it'll go in that direction like that. We can simplify this because this electric field strength is opposite to this electric field strength. That'll cancel out, the equal and opposite. This electric field strength is equal and opposite to that electric field strength. They will cancel out. So the resultant electric field strength is actually 2 times magnitude of the electric field strength we calculated in part 1. So our answer is 2 times K. I'm going to write this down here just now, and I'll explain where that comes from in a minute. 3.2 times 10 to the minus 6, of course, represents the fact that it's a microcoulomb, and 0.15 squared is distance A squared. That's going to give us an answer of 2.6 times 10 to the 6 newtons per coulomb. That is the units of electric field strength. So let's remember them. It says the magnitude of Q is there. Determine the magnitude, we've done that, and the direction. So we have to say the direction is towards the bottom right charge. And that's good enough for describing the direction. Now, why did I say K is 8.99 times 10 to the 9 and just leave it at that? Well, K is actually equal to 1 over 4 pi epsilon naught. And epsilon naught is a permittivity of free space. 4 pi is just a number. The permittivity of free space is given as 8.85 times 10 to the minus 12. And there's loads of units in here. It's like, let me see if I can remember. C squared, n to the minus 1, meters to the minus 2. That is what the permittivity of free space is. And it's how easily fields can travel through free space in its simplest form. If we pop all those numbers in, then what we get is 8.99 times 10 to the 9. So instead of writing this whole equation with 1 over 4 pi epsilon naught on it, we just use the constant k, and it's easier for us to remember that k is equal to 8.99 times 10 to the 9. Question 2. 3 fixed charges plus q, and minus 2q are at the vertices of an equilateral triangle. What is the resultant force on an electron at the centre of the triangle? We've said it's equilateral. That means we know that the distances between the electron and all the charges is the same. Great, we can start off with that. Now what we're going to do is we're going to use a ruler, and we're going to draw a representation vector arrow showing the electric field strength felt by the electron due to each of these 3 charges. We'll start with this positive Q here. The electron is negative, this is a positive charge, so the electron will be attracted towards that charge. And we're going to give this vector arrow a representation line of 2 centimetres towards that charge. Great, now let's go to minus 2q. This electron is going to be repelled by this minus 2q. So the electron is going to feel an electric field strength repelling away in that direction. It's going to feel 2 times the length of the arrow before. But because it's vectors, we're going to add it tip to tail. So 1, 2, 4. That's what the electric field strength felt by the minus 2q added tip to tail to the original one. Finally, we're going to look at this one. The electron is going to be repelled from there. It's going to be repelled in that direction. And it's going to be repelled by the original length. The magnitude is going to be half of that one that we've just done. Great. Now what we want to do is find the resultant vector. We go from the electron to the end of the final arrow, and we draw an arrow like this. So the resultant field strength felt by the electron is in that direction, which gives us an answer of B. This is a higher level question. A negative charge moves in an electric field. Equipotential lines for the field and 4 possible paths of the charge are shown. Which path corresponds to the largest work done on the charge by the field. We know that work done is equal to QV, and the charge is the same for them all. So the most amount of work done will be the biggest potential difference experienced. So that rules out C and D. We're looking at either A or B. We're looking at work done on the charge, and the charge is a negative charge. So we're going to have to do work to bring it this way, whereas this is going to be work done by the charge. So the answer is B. Question 4. A -5 microcoulomb charge and a +10 microcoulomb charge are a fixed distance apart. Where can the electric field be 0? Let's look at each charge and consider the electric field due to each of those charges. We'll go with the 10 microcoulombs first. A positive test charge would be repelled from this 10 microcoulombs. Let's draw the field lines representing for that. So I'm going to go along to 1, 2, 3, 4 centimetres across, and it's going to be felt that way. Given that we're only looking in one direction, there's going to be an electric field strength in that direction too. And I've just used 4 centimetres as just a representation. The 5 microcoulomb charge is also going to have an electric field. We'll draw that in red. It's going to be smaller in magnitude, and it's going to be in the opposite direction because a positive test charge is going to be attracted towards that 5 microcoulombs. It's going to look like that. Let's look at position 1. If we were to place a positive test charge there, it would feel an average force, let's just use the word average force, in that direction. And it would feel a very weak force, very, very weak force in that direction, because we're still feeling the effects of this electric field strength. It's just very weak. Let's go to position 2. We'd feel quite a strong force in that direction, and it would also feel a strong force in that direction too. Finally, in position 3, it would feel a weak force in that direction and a weak force in that direction. The position where it's most likely to average out to 0 or add to 0 is position 3. This would be very strong in that direction, and this would be probably stronger in that direction. So I'm going to say it's C, position 3 only. Question 5, and this is higher level only. 2 parallel metal plates are connected to a DC power supply. An electric field forms in the space between the 2 plates as shown. We can see here that this is a positive side and this is a negative side, and we know that because the electric field strength is going from positive to negative. What is the shape of the equipotential surface that result from this arrangement? The equipotential surfaces are always at 90 degrees to the field lines. So we know that the equipotential surfaces within side here will look like that, and they'll be equally spaced. Then as we get to the endpoints here, keep them at right angles to the field lines, we'll have to angle them out slightly. And you can see that that would be a right angle there, and similarly down here. It'd have to be angled out slightly. And it's all right angles here. So we're looking at B.
Question 6 is higher level only. An electric field acts in the space between 2 charged parallel plates. One plate is at 0 potential and the other is at potential plus V. The distance x is measured from point P in the direction perpendicular to the plate. What is the dependence of the electric field strength E on x, and what is the dependence of the electric potential V on x? Let's look at the electric field strength first and draw the electric field lines. They are equally spaced. They're straight lines. Drawn these equally spaced as I possibly can. And they go in the direction a positive test charge would take. Just as an aside, let me just do a quick aside here. Let's say we have a positive charge here, and these field lines would go radially outwards. The electric field is strongest closest to the charge because the electric field lines are closer together. And out here, the electric field lines are further apart, which means the electric field is weaker. When we have a uniform field, then the electric field is constant at all points because the field lines are the same distance apart at all points. So, for the answer on how does the electric field strength depend on X? Well, it's constant. So we're looking at answer B. If we want to convince ourselves that answer B is correct, let's think about potential. E is equal to V over D. And in this case, D is the distance between the two plates. So E is equal to V over X. V, let's rearrange for V, is equal to E X. E is a constant. So V is proportional to X, which tells us that B is absolutely correct. The answer is B.
Question 7. 2 point charges are at rest as shown. At which position is the electric field strength the greatest? We're going to do this again. We're going to take our ruler and draw a representation of what the electric field strength due to each charge would be. Plus 5 microcoulombs means that a positive test charge would be repelled, and it would be repelled, let's just say it's 6 units across. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's a representation of the electric field strength due to the plus 5 coulombs. Let's look at the representation of the field strength due to the minus 2.5 coulombs. It would be attracted, and it would be half the amount that we gave to the plus 5 coulombs. It'd be like this. Let's consider each point A, B, C and D and consider the effect of the electric field strength due to each charge. At point A, it's going to feel force in that direction from the 5 microcoulombs, and it's going to feel a very weak force in that direction due to the minus 2.5 coulombs. At B, it's going to feel quite a strong force in that direction due to the plus 5 coulombs, and it's also going to feel a strong force in that direction due to the minus 2.5 coulombs. So this is a contender so far. Let's look at D. D is going to feel a very weak force in that direction due to the plus 5 coulombs, and it's going to feel a strong force in that direction due to the minus 2.5 coulombs. Finally, at C, it's going to feel a weak force in that direction due to the plus 5 coulombs, and it's going to feel a relatively strong force in that direction due to the minus 2.5 coulombs. If we add them together, it looks alright, but I reckon our biggest, strongest point is here. So our answer for question 7 is B. Here we have another question very similar. The diagram shows 2 equal and opposite charges that are fixed in place. At which points is a net electric field directed to the right? If we go to minus Q, positive test charge is going to be attracted towards it, so the electric field strength is going to be in that direction. And for the plus Q, a positive test charge is going to be repelled, and it'll have the same magnitude as the other one because it's the same size of charge. For each X, Y and Z, let's now look where we expect the resultant force to be. For X, we're expecting a large force in that direction per test charge due to the electric field, and a weak one in that direction due to the positive charge. So is this electric field strength directed to the right? Yes. Why? I'm going to look at a very weak electric field strength in that direction and a much stronger electric field strength in that direction. So yes, that is net right as well. So I'm looking at question 8C. Question 9 is higher level. A charge of minus 3 coulombs is moved from A to B and then back to A. It's A to B. Let's move from A to B and then back to A. The electric potential as A is plus 10 volts and the electric potential at B is minus 20 volts. What is the work done in moving the charge from A to B and the total work done? If we take the total work done first of all, the charge is moved from A to B and then back from B to A. The charge starts here and it ends here. It ends on the same equipotential line. If it's on the same potential line, then no work is done. So the total work done is equal to 0 joules. Our answer is either A or C. If we're looking for just A to B now, A to B, the work done, we're going to use W equals QV. Q is equal to minus 3 coulombs. V is equal to minus 30. So 3 times 30 is 90 joules. The answer is C.
Question 10. The diagram shows magnetic field surrounding two current-carrying metal wires P and Q. The wires are parallel to each other and at right angles to the plane of the page. What is the direction of the electron flow in P and the direction of the electron flow in Q? So for this, we're going to use the right-hand screw rule. Right-hand screw rule, and the thumb, I'm going to try and draw this here. The thumb goes in the direction of conventional current, which is positive to negative, and the fingers curl around in the direction of the field lines. That's supposed to be a hand, and these are supposed to be fingers, and that's the wrist. Okay? So if we're looking at this right-hand screw rule and we have the conventional current going into the page like that, into the page, then we point your thumb in that direction into the page and your fingers will curl round in that direction. If we have your thumb pointing out of the page like this, if you take your thumb and point out of the page with your right hand, your fingers will curl in that direction. Right, let's take that. And remember, this is conventional current. What I'd like you to do is look at P. We want the fingers to curl anti-clockwise. So is your thumb going to be pointing into the page or out of the page? You do it for me now. My thumb, personally, is pointing out of the page. So P is out of the page for conventional current. But we're not looking at conventional current. We're looking at direction of electron flow, which is opposite to conventional current. So even though our thumb is pointing out of the page, the direction of electron flow is into the page, so we've got to have either A or B. Let's look at Q. Which direction of your thumb pointing into the page or out of the page will cause the magnetic field lines to be clockwise? Well, it's into the page. So at this point, we're going to point our thumb into the page, which is a conventional current. So the electric flow current is opposite to that, which is out of the page, and the answer is B. Question 11 is higher level only. An isolated hollow metal sphere of radius r carries a positive charge. Which graph shows the variation of potential V with distance x from the centre of the sphere? I'm going to take a little bit of time here to talk you through the idea of a hollow metal sphere. We have a hollow metal sphere up here, and it's positively charged. That means the charges are equally spaced around the edge of this hollow sphere. They're equally spaced because they all carry the same electric field and they all repel each other in an equal fashion. Because they all carry the same electric field and they all repel each other and they're all opposite each other, then what we find is that inside this hollow metal sphere, the electric field is 0. However, the potential is not 0. It's constant and it's not 0. You just have to trust me that inside a hollow metal sphere, potential is not 0 and it's a constant. That means we're looking at answers A or B, because within this sphere here, you can see that V is not constant. And within this sphere here, you can see that V is 0, so it's not that one either. Then we have to look at how does potential vary with distance from the centre of a sphere. Well, potential is given by KQ over R, and R in this case is X, distance X. V is inversely proportional to X, meaning we're going to find this sort of concept as the distance increases away from the centre of the sphere. And the graph for A or B that most closely resembles that is B. The answer is B. The takeaway here for me is these two concepts here. The electric field is 0 inside a hollow metal sphere, but the potential is not 0 and it is a constant value. Question 12. A non-uniform electric field with field lines as shown exists in a region where there is no gravitational field. We're only dealing with electric field. X is a point in the electric field. The field lines and X lie in the plane of the paper. A. Outline what is meant by electric field strength. It is the force per unit positive test charge. That's enough. That's all we need to write. B. An electron is placed at X and released from rest. Draw on the diagram the direction of the force acting on the electron due to the field. Okay, well we know that the field lines go in the direction that a positive test charge would take. That tells us that this is a positive side and that is a negative side. If we're suggesting that X is an electron, that makes it negative, it's going to be attracted towards the positive and repelled from the negative. So the electron is going to feel a force to the left in that direction. C. The electron is replaced by a proton which is also released from rest at X. Compare, without calculation, the motion of the electron with the motion of the proton after release. You may assume that no frictional forces act on the electron or the proton. So the first thing I'm going to say is when you're asked to describe the motion, you want to use one of 4 terms. You want to use constant velocity, you want to use stationary, acceleration, or deceleration. And in this case, we're obviously going to look at acceleration. It's not going to stay constant because it's experiencing a force. The other thing that stands out about this question is the idea of compare it with the electron and the proton. And I'd like to really have a look at quickly, before I write anything down, what the differences between an electron and a proton are. Well, an electron is a negative charge and a proton is a positive charge. A proton is heavier, it's got a greater mass, and an electron has a small mass because the mass of an electron is 9.11 times 10 to the minus 31, which is tiny, and the mass of a proton, I don't know if I can remember this, is 1.67 times 10 to the minus 27 kilograms. I think that's all we need to know. Okay, so we've compared the electron and proton, we know we've got to use the word acceleration, and we've got to get 4 marks. So the first difference in the motion will be the electron will accelerate to the left. We have the force on the electron above that's going to the left. The proton will accelerate to the right. Another difference, A equals F over M. The charge on each electron is the same, and the charge on the proton is the same. And the force, when we're looking at electric fields, is E equals F over Q. So F equals EQ. So the force felt by the electron and by the proton is the same. However, the mass is greater for a proton. The magnitude of acceleration for the electron will be greater than on the proton because the force is the same, but the proton has a greater mass. For the fourth mark, we have to look back. The electron is moving towards the left, and you can see that the field lines are getting further apart. That means that the electric field strength is lessening at this point. The proton is moving to the right, and you can see the electric field lines are getting closer together. That means the electric field strength is increasing. So they're not going to accelerate constantly. The electron is going to experience a smaller magnitude of acceleration as it moves to the left. The proton is going to experience a larger magnitude of acceleration as it moves to the right because F equals EQ, and as this increases, then the force on the proton increases. So let's go back to number 4. Both particles will increase in speed. However, the electron will experience a lower magnitude of acceleration as it moves away. My writing is dreadful. From X. Conversely, proton has increased acceleration due to electric field getting stronger. I'm so sorry about my writing here. Question 13. An ion of charge plus Q moves vertically upwards through a small distance S in a uniform vertical electric field. The electric field has a strength E and its direction is shown in the diagram. What is the electric potential difference between the initial and final position of the ion? Okay, the potential difference is, we're going to use this equation here. It's actually not much simpler than this. E equals V over D. This is for a uniform electrical field. V is equal to E, D, and D is the distance, so V is equal to E, S. Yes. C. Don't overthink it. If you see uniform electric field, always write this down and see if you can use that first. Question 14. 4 identical positive point charges of magnitude Q are placed at the vertices of a square of side 2D. What is the electric potential produced at the centre of the square by the 4 charges? We want to find out what the potential here is. Potential is a scalar. You just add them up. You don't have to do any vector addition. So let's find what the potential due to 1 charge is at the centre. And to do that, we need to find the distance from here to there. We're going to do that using a right angle triangle. So let's redraw that right angle triangle here. That's 2D. That's 2D. And we want to know the distance halfway along there. This is 45 degrees. So let's use sine 45 equals 2D over this distance here. Let's call it x. So x is equal to 2D over sine 45. Sine 45 is root 2 over 2. So we'll do root 2 over 2, but we take that up to there. So we've got x is equal to 4D over root 2, but we only want half of that. So half of x, and this distance here that we're looking at is going to be 2D over root 2. Let's now work out what the potential is. The potential is V equals KQ over R. In this case, it's 2D over root 2. That goes up, so it's root 2 up there. That's the potential due to 1 charge. We want 4 of them, so we have 4V is equal to times 4. We have 4 root 2 KQ over 2D. Let's cancel that with that. So we've got 2 root 2 KQ over D. The answer is D. Question 15. The diagram shows some of the electric field lines for 2 fixed charged particles X and Y. X must be a positive charge because all the field lines are moving away from it, and Y must be a negative charge because the field lines are moving towards it. The magnitude of the charge on X is Q, and that on Y is small q. The distance between X and Y is 0.6 metres. Draw that in. And the distance between P and Y is 0.82 metres. I know it's the 3 significant figures, I just can't be bothered with that. At P, the electric field is 0. Determine to 1 significant figure the ratio Q over Q. If the electric field is 0 at P, that means the electric field due to X is equal and opposite to the electric field due to Y. So EX equals EY. We're going to use the equation for the radial field strength, which is KQ over R squared. So EX is equal to KQ, X is Q, okay, over the distance from X to point P is 0.6 plus 0.82 all squared. And the electric field strength equation for Y is going to be K small q over 0.82 all squared. Cancel out the k's and let's cross multiply. So we've got Q 0.82 squared equals small q 0.6 plus 0.82 all squared. Now we want to bring it down to the ratio of Q over Q, and that means the answer will be 0.6 plus 0.82 all squared over 0.82 squared gives us an answer of 2.998. We wanted to 1 significant figure. The answer is 3. Question 16. An electron is placed at a distance of 0.4 meters from a fixed point charge of -6 millicoulombs. A. Show that the electric field strength due to the point charge at the position of the electron is 3.4 times 10 to the 8 newtons per coulomb. Okay, well, E equals KQ over R squared. You'll remember from question 1, we're saying that K is equal to 8.99 times 10 to the 9. Q is the charge on the fixed charge, which is 6 times 10 to the -3. You'll notice I haven't put minus in there. We're really just looking at the magnitude of it, so we don't need to put the direction in. And R squared is 0.4 squared. Let's plug all of that into our calculator, and that gives 3.37 times 10 to the 8 newtons per coulomb. We're going to give everything to two significant figures, so 3.4 times 10 to the 8 newtons per coulomb, which is what the question asked. B1. Calculate the magnitude of the initial acceleration of the electron. A equals F over M, and F, remember here, E is equal to F over Q, so F is equal to EQ. So instead of putting F up here, we'll put EQ over M. The electric field is 3.4 times 10 to the 8. Charge on the electron is 1.6 times 10 to the -19. The mass of an electron is 9.11 times 10 to the -31. Find that from the data booklet. And that gives us an answer of 5.97 times 10 to the 19 meters per second squared. I think that's a bit too many significant figures, so we're going to do 6.0 times 10 to the 19 meters per second squared. B2, describe the subsequent motion of the electron. Do you remember earlier I said when it described the motion, you're looking at using one of those 4 phrases. In this case, again, we're going to use acceleration. But we've got to give it 3 marks. We're going to say it's accelerate. We're going to say that it's going to accelerate to the right because it's going to be repelled from the charge. The acceleration is going to decrease because the force is going to decrease as it moves away from that charge. So the magnitude of acceleration decreases, but the speed still increases. It's still increasing its speed, it's just not increasing as much because the magnitude of the acceleration decreases. You can put that into sentences if you want, but it'll accelerate to the right. The magnitude of the acceleration will decrease as it moves away from the charge, but the speed will continue to increase. There's your answer. Question 17, higher level. The diagram shows the electric field lines of a positively charged conducting sphere of radius r and charge q. So, because it's a conducting sphere, whether it's hollow or solid, we have to assume that all the positive charges will be equally spaced and placed around the surface of this sphere. That's because the charges are free to move and the positive charges will equally repel each other, meaning they'll all be equally spaced. This takes us back to what we were talking about earlier with this sphere. Positive charges, I don't have to draw again. You get the idea, right? And do you remember I said the electric field inside this is 0 because they're all equally in opposite spaced, all equally repelled. That means that the resultant electric field is 0 and the potential within that sphere is non-zero and it's constant. We saw that from the graph earlier. Okay, points A and B are located on the same field line. Explain why the electric potential decreases from A to B. You can imagine if we take a positive charge and move it towards a positive charge, then work must be done on the charge. However, if we're taking that positive test charge and move it in the opposite direction, work must be done by the charge. That means that the potential must be decreasing. Why is it decreasing? Well, at A, it sits on an equipotential surface here, and B sits on a different equipotential surface. And work is done when we move charges between equipotential surfaces. Let's put this into the explanation. Work is done when a charge moves between equipotential surfaces. A and B are on different surfaces. Our second point will be in moving a positive test charge from infinity to point A, work must be done on the charge. However, from A to B, which is away, work is done by the charge. B. Draw on the axis the variation of electric potential with distance r from the centre sphere. Remember I told you that within the sphere, is it up there, electric field is 0, V is non-zero and constant. So we're going to have a nice straight line to the edge of the sphere. And then if we look at the formula for V, it's KQ over R. This means that V is proportional to 1 over R. It's inversely proportional. So we want to draw a nice inverse proportion curve. Point R. There's our graph. C. A proton is placed at A and released from rest. The magnitude of the work done by the electric field in moving the proton from A to B is 1.7 times 10 to the minus 16. Point A is at a distance of 5 times 10 to the minus 2 from the centre of the sphere. Point B is a distance of 1 times 10 to the minus 1 from the centre of the sphere. C1. Calculate the electric potential difference between points A and B. W equals QV. So V is equal to W over Q. W is 1.6 times 10 to the minus 16. Q is the charge on a proton, which is 1.6 times 10 to the minus 19. Our potential difference is 106 to 0.5 volts or joules per Coulomb. Let's give it down to two significant figures. So it's 1100 volts, or the units can be joules per Coulomb. C2, determine the charge Q of the sphere. This is pretty tricky. I think what I'm going to do is going to say the change in voltage is equal to KQ over the change in distance. Now that's a little bit different from the equation we're used to, but given that we're looking for the change in voltage and we have a change in distance, that's the only thing I can think of really. So great, so let's pop the numbers in. 8.99 times 10 to the 9. Of course, we said K was equal to that in a previous question. We don't know what Q is. We do know the change in distance is equal to 5 times 10 to the minus 2 minus 1 times 10 to the minus 1. And we know that the potential difference, delta V, is equal to 1100 from the previous question. So we're going to rearrange to try and find out what Q is. Q is equal to 1100 times 5 times 10 to the minus 2 minus 1 times 10 to the minus 1. And it's all divided by 8.99 times 10 to the 9. I've just rearranged that to find out what Q would be. We pop all those numbers in and we get 1.2 times 10 to the minus 8 coulombs. We could make that 12 nanocoulombs. D. The concept of potential is also used in the context of gravitational fields. Suggest why scientists develop a common terminology to describe different types of fields. Because it's so easy to compare. Did you see in step 1 mass of the majority, we drew that comparison table for electric fields and gravitational fields? And the concept is if you understand it in, say, gravitational fields and we use the same terminology, then it's going to be easier for you to understand it in electric fields. So the reason we use common terminology is to easily compare and contrast different types of fields. Now, I suspect you're going to say to me, how did I know to write that down? And I didn't, but it's worth 1 mark. So if you really can't think of anything to write down there, it's not directly in the syllabus, give it your best shot and move on.